Good morning. We are going to go to our third lesson in the counting or combinations and permutations unit. On Friday, we covered the idea of how to deal with arrangements if you had non-distinct items. If we look at the word permutations, we see that we've got two T's, and those are going to cause us some problems. If we had 12 distinct objects, we could arrange this as 12 factorial, but we don't have the 12 distinct objects. We have two T's that are exactly the same. So we have to divide by those two T's, because if I flip these two T's in this arrangement, it's still going to say permutations, and it's going to be the same thing throughout. The same thing with arrangements down here. We have two A's, two R's, two E's, and two N's. So we have, again, 12 letters in the word arrangements. Because we have two A's, I have to divide that by 2 factorial. Two R's, divide by 2 factorial. Two N's, divide by 2 factorial. And two E's, divide by 2 factorial. Hence this formula up here, the number of ways to arrange an object with items that are exactly the same are n factorial, the number of items, divided by the number of repetitions factorial, and as many times as you want. So applying this to problems, we can do this in the same way. Here we're talking about blocks instead of words. We have 6 red blocks, 4 blue blocks, and 2 green blocks. One way to think about that is to create arrangements of letters. So we can see this. What we have here is, again, 12 objects. So if there were 12 different colored blocks, we would go 12 factorial. These 6 red blocks have to be dealt with by dividing by that by 6 factorial. The 4 blue blocks have to be dealt with by going dividing by 4 factorial, and the same for the 2 green blocks. This idea of creating an arrangement of letters or creating an arrangement of things, and then how many ways can we arrange them, is a very useful tool, and it actually takes away what we're talking about here, permutations and combinations, and just doing it with this arrangements with repetitions. Here we have a question that's going to show up a lot. It's a committee question. We're going to do this in both combinations and permutations, but we're going to do it here first. The committee of 4 is to be named up from a 16-person student council. How many arrangements are possible if the committee has a chair, a vice chair, a secretary, and a treasurer? So if we think about what we're actually doing here, is we're putting one person as the chair, one person as the vice chair, one person as the secretary, one person as the treasurer, and the remaining 12 people get to be lucky. They don't have to sit on this dang committee. Now, I'm just putting the tick marks there so I can count. What we have here is we have 16 letters, 16 people in this situation. 4 of them that are going to be on the committee, and each of those 4 people will have a job. And 16 people that don't have to do anything because they're not on the committee. So if we look at this and treat this as a permutations with repetitions or arrangements with repetitions, if they were all separate letters, there would be 16 factorial ways. If we were putting 16 people on a committee, which everybody had a job, we could do 16 factorial ways. We have over here 1 factorial, 1 factorial, 1 factorial, 1 factorial for our C, V, S, and T. Most often, we do not put those guys in. And that leaves us with our 12 lucky people. So what you'll see this one here written as is 16 factorial over 12 factorial. Again, do I don't really want to know what the number is? Not particularly. I'm sure we can all work with a calculator. So I created an arrangement of things, or a group of letters that corresponds to the committee. This idea of a group of letters and then talking about arrangements with repetitions is a very powerful tool. Here we have no restrictions. So that means 4 people will sit on the committee. They won't have any jobs, but they will sit on the subcommittee. And that still leaves our 12 lucky people. Okay. So here we have 16 factorial, as we did before. In this case, the 4 people on the committee, doesn't matter how much we put them on or when they put them on, there's 4 people that will be sitting on that committee, and there will be 12 people that are not sitting on that committee. We've broken down this problem to a 16-person word with 4 C's and 12 L's. If we take a look at Bob, Bob must be on the committee. So now we are breaking this down into Bob and the rest. There's one way to put Bob on the committee. Okay. Now, what does this change? Well, now that changes. There's only 3 people left to put on the committee from the remaining 15. And I'm getting tired of writing L's out, so I'm just going to say there's 12 L's there. So we have one way to put Bob on the committee, and we have our 15 factorial, because we've taken Bob out of the group that we now have to put on the committee. 3 more people will go on the committee, and 12 that will not. Since it's Bob and the rest of the committee, we are going to multiply those together. Because again, what we have here is our fundamental counting principle. We're putting Bob on the committee, and then we are picking 3 more people to put on the committee. With this one here, Bob or Carol must be on the committee, but not both. Okay. Now, what this means is we are dealing with a group of Bob or Carol, and then we have the rest. There are 2 people from Bob or Carol. There is 2 ways to put them on. Either I put Bob on the committee or I put Carol on the committee. I can't have both on the committee for some reason. Maybe they're married. I don't know what the reason would be. So we can put Bob or Carol on the committee. Now we have to figure out the rest. Well, now we have, again, we still have 3 people left to place on the committee in addition to Bob or Carol. And the thing is here, this is only going to be 11 people that are going to be lucky. Because one of the Bob or Carol are going to be lucky, so they're not sitting on the committee. We've taken them out of the pool from the rest. The rest is now only 14 people big. 3 people will go on the committee, and 11 will not. So here we have 14 factorial for the objects, but since 3 are exactly the same, they're going on the committee. That's what I mean by exactly the same. And 11 are not going on the committee. They get to be lucky in addition to either Bob or Carol. And again, since we're putting Bob or Carol and then placing the remaining 3 people on the committee, we are going to do the multiplication. Same question here. We've got a debating team. Difference is now we've got 2 groups of people that we may have to consider within the question. We have to make sure that maybe those groups of people are important to the question. Now, first part A, four members each assigned a job on the team. So we're talking about a group of four, or four people on a committee that each have a job. I'm just going to call it first position, second position, first, second, third, and fourth. Okay. And then the remaining people, which we have 15 total, the remaining 11 are not on the team. So this is what we're going to be trying to arrange. We've got four distinct positions, and then we have 11 people who are not chosen for the team. The grade 8 or grade 11, grade 12 students don't matter in this situation because the question just says four people assigned. We don't have to worry about grade 8, grade 11, and grade 12. So here we have our 15 objects. 11 of them are not on the committee, so 11 ends. Now for these guys here, we could put 1 factorial, 1 factorial, 1 factorial, 1 factorial. Notice, if I do that, the sum of the numbers on the bottom are going to add up to the top number. 1 plus 1 plus 1 plus 1 plus 11, 15, we have 15 on the top. So when you're talking about doing this with distinct jobs or arrangements again, each of these are a specific job. We do it this way. We are still doing the same thing. We're just checking to make sure that they add up to the top guy. We have our 1 for the first position, 1 for the second position, 1 for the third, and 1 for the fourth position. 4 members with no jobs. Well, that changes my word. Instead of first, second, third, we're just going to say 4 people on the team and 11 people are not on the team. 15 factorial over 4 factorial, 11 factorial. Again, we add up to our denominator adds up to our numerator. With the next question, 4 members, only one of whom is in grade 11. So now we have to talk about the grade 11 kids and the grade 12 kids. We have to treat them separately. Now, if I have my grade 11, which I believe was 7, I have to check. Okay, so we got 7 grade 11s to choose the one person from. Out of grade 11, one person will be on the team. 6 will not be on the team. So the ways to arrange that is 7 factorial over 6 factorial, 1 factorial. Again, we add up. Now the grade 12s, that means that we have 3 people from grade 12 that are on the team, followed by 5 people who are not on the team. Here we have 8 factorial over 3 factorial, 5 factorial. Now again, since we are doing this, we're putting a grade 11 on the team, and then we are also putting a grade 12 on the team, or 3 grade 12s. It is a multiplication because we're doing the grade 11s, and then we are also doing the grade 12s. Bubba must be on the team. He's a grade 12. We need 2 other grade 11s, or grade 12s, and 2 grade 11s. So here we divide this up to Bubba, grade 11, grade 12. And since we are doing this, we are doing this, putting Bubba and then grade 11s and then grade 12s, we will be multiplying these. Well, there's one way to put Bubba on the team. He is on the team. 1. Grade 11s, we still have 7 grade 11s. 2 of them will be on the team. 5 of them will not be on the team. So we have our 7 factorial over 2 factorial, 5 factorial. Now our grade 12s have changed. We are going to have 2 other grade 12s on the team. But as we've removed Bubba from the group of people in grade 12, we only have 5 other people who are not going to be on the team. Because we've taken Bubba from the group of grade 12s and put him in a separate group. So that means we have less people in grade 12. So again, here we have 7 factorial, 2 factorial, 5 factorial. Again, as I said, multiplication, because we are doing that one after the other. They're all on the same team. Now, when we get into this concept of at least or at most, I found that it's really a really good problem-solving strategy is to list all the possible ways you can do it, and then think about what you have, what does the question mean. So here we're going to use the above. There must be at least 4 grade 12 students on a team of 5. So what we have here, we have a team of 5. We could have 5 grade 12 students, no grade 11s, 4 grade 12s, 1 grade 11, 3 12s, 2 11s, 2, 3, 1, 0, and 1, 4, and 0, 5. So there must be at least 4 grade 12 students on the team of 5. So this means we have 5 grade 12 students and no grade 11s, or 4 grade 12 students and 1 grade 11. So 5 grade 12s, or 4 grade 12s, and 1 grade 11. So if we treat them like this, we are going to have to do both of these, and then we are going to add them together, because it's either going to be the 5 grade 12s, or it's going to be this. They can't happen at the same time, so we have to add them together. So our 5 grade 12s, 5 people on the team, and 3 not. So that's our grade 12s. And our grade 11s, we have nobody on the team, and 7 that are not. So we have our 8 factorial, because we had 8 grade 12s. 5 of them are on the team, 3 of them are not, multiplied by 7 factorial, 7 grade 11s, with nobody on the team, and 7 people on the team. And this is the reason why we define 0 factorial as 1. Over here, we have 4 grade 12s on the team, 4 not on the team. We have 1 grade 11 on the team, and 6 not on the team. So we are going to go 8 factorial over 4 factorial, 4 factorial for our word up there. And again, multiplying it in this case to 7 factorial over 1 factorial, 6 factorial. And again, I don't care too much about what the answer is, but we are breaking this up into this at least, or in this case, at least 4. So we have our 5 grade 12s, no grade 11s, and then 4 grade 12s and 1 grade 11. We add them together because it's one or the other. They can't overlap. What we have, if you think about this in a tree diagram, you have your 5 grade 12s over here, and your 4 grade 12s over here, but there is a wall between them. right? We can pick this guy, then we can do this and so forth. But they don't, these two trees don't overlap. So we have to do this one or we have to do this one. And I have no desire to do this one by a tree diagram, by the way, but a tree diagram does get the idea across to you. They don't, they aren't the same part as each other. They're completely separate trees. So we have to add them together. Okay, now must contain at least one grade 12. Now, at least one grade 12 is everybody in that box. That's 1, 2, 3, 4, 5 separate calculations. Well, actually 10 calculations. But you notice what we have here is this entire thing that I am just about to circle, I hope, this entire thing is a listing of every possible committee there is out there. Every committee that we could choose or make is going to contain one of these 6 options. So you notice what's missing from that total in that red box. There's only this guy here, no grade 12s and 5 grade 11s. So what we can do here is take the total ways to do this and subtract the ways that we don't want. I really don't want to do 10 separate calculations for this. Much easier to do like 2. So the total ways, no restrictions, 15 factorial, or 15 factorial, 15 people that can be arranged. 5 of them will be on the committee, 10 of them will not be on the committee. That's just how many different ways can we make a committee of 5 from 15. We're going to subtract that, from that, we're going to subtract when we have 0 grade 12s and 5 grade 11s. To subtract that. So again, because we're doing 0 grade 12s and then putting 5 grade 11s on, we are going to multiply that guy. So 0 grade 12s would be 8 factorial over 0 factorial, 8 factorial, which is just 1. So you don't actually have to write it down. 5 grade 11s, 7 factorial over 5 factorial, 5 people on the committee and 2 that are not. So going back to what I was doing before, there are no grade 12s on the committee, and there are, or team, I guess, in this case, and there are 5 on the grade 11s on the committee and 2 grade 11s not on the committee. Hence where I get those numbers from. Where is the breakdown? Where do I do this compared to the other one? Well, probably at this point, if I'm saying at least 2, I'm still going to do it this way. At least 3, it's the same number of calculations either way. Now, on your homework, you're probably going to see a lot of card problems. It's a very common way that we do this. You won't see it on the diploma because cards are not, we have always taken card problems off because not everybody plays with playing cards regularly. Most of us don't anymore, myself included. So just a quick reminder, there are 52 cards in a deck. There are 4 suits, diamonds, hearts, spades, and clubs. Clubs and spades are black, so there's 26 black cards, 26 red cards, and there are 12 what we call face cards, i.e. those that have a face on the card. So we're going to use these on the next problems here. We want to, how many 5-card hands consist of exactly 3 aces? What we have here is we have 2 categories. We have aces, and then we have other cards. Because we have a 5-card hand to fill. We want exactly 3 aces, and then we want to fill the other cards, or the other part of the hand, with 2 other cards. Now we know there are 4 aces in a deck. That leaves there are 48 not aces in a deck, 48 other cards. So here we have 3 aces in a hand, 1 that is not. We have 2 of the other cards that are in a hand, and 46 that are not in that hand. So same principle, 4 aces, 3 in a hand, 1 that's not, times, because we're filling the remaining, for each one of these 4, each one of these 4 possibilities, there are all of these possibilities that can be matched up with them. So here we have our 48 factorial times 2 factorial, 46 factorial. So again, we're breaking this up. Before we get to the math, we have to worry about the problems. We have 3 aces and 2 kings. Well, we need 3 aces from the 4 that are in the deck. We need 2 kings from the 4 kings that are in the deck. We are already dealing with all of the 5s, or all 5 cards in that hand. So there are no others in this case. 0 others. So I'm going to just ignore that, because we filled up the 5-card hand already with the 3 aces and 2 kings. So our 3 aces stays the same as before. And then our 2 kings in the hand, 2 that are not. So we have our 4 factorial over 3 factorial, 1 factorial times 4 factorial over 2 factorial, 2 factorial. And this gives you an idea why a full house is ranked higher in poker than 3 of a kind. You can definitely see there's a lot more hands that have 3 aces in them than there are that have 3 aces and 2 kings. This is going to be just, where am I? This is just going to be 6, and that's going to be 48 times 47 divided by 2. So big numbers. At least 2 kings. So again, we have our kings and we have our others. We could have 4 kings and 1 other, because it's a 5-card hand. 3 kings and 2 others. 2 kings and 3 others. 1 king, 4, 0, and 5. So the at least 2 kings is this one. Now, again, here, what do I do? Well, I got 3 times 2 calculations, so I got 6 calculations here. I'm going to have 5 calculations there. It really doesn't matter which way you're going to do this. I'm going to do it total minus what we're trying to avoid. So the total would be 252 factorial. So we have 52 cards in a hand, 52 cards in a deck, I should say. So 5 cards in that hand, 47 cards not in that hand. 52, 5 factorial over 47, or times 47 factorial, minus these guys here. So same principle as before. If we have 1 king, 4 others, We have 1 in the hand and 3 that are not. So that's going to be 4 factorial over 3 factorial, 1 factorial. We have 4 of the others in a hand, and that will leave 44 not in the hand, because we have 44 plus 4 that are in the hand plus 4 kings. That gets us to 52. So times 48 factorial over 4 factorial, 44 factorial, plus, so if I now have 2 kings, and that means we have 3 others. Now we have 45 not in the hand for the others. 4 factorial over 2 factorial, sorry, no, I'm going backwards, I'm sorry. So we did 1, now I need 0. That was the problem. Okay, sorry about that. I was going up instead of down because I'm looking at these two. So I did 1 and 4, now I have to do 0 and 5. So that means we have 5 others in a hand and 43 not in that hand. So plus our, so we have 4 factorial over 0 factorial, 4 factorial times 48 factorial, 5 factorial, 43 factorial. Now that's one way to do it, and the other one would be just do all 3 of these. You notice it's the same, essentially the same number of calculations doing the total minus what we're trying to avoid, or just doing what we're trying to figure out. So in that case, either is fine. So we'll go over this tomorrow or when you get into class. So that is your homework for today, just to watch the video. I'm going to put one more video for you to watch. I will put these notes, both the completed and uncompleted, on the classroom for you so you can work through them. I shall see you tomorrow.